Hello class, in lesson 2.4, dividing polynomials, you'll learn how to use long and synthetic division to divide polynomials. Let's get into the first example and use long division. So here we're going to set up our long division problem by creating an inside-outside box. So we have again our x minus 2 on the outside, our divisor, and inside our division box we're going to write our polynomial of x to the third plus 4x squared minus 16x plus 8. So we set up long division again, just like polynomials, just like normal long division. So we have our inside and our out. And what we're going to do is simply focusing on the leading term of our divisor and our dividend and divisor. We're going to just simply see how many times can x go into x to the third power, which in other words simply implies what is x to the third power divided by x. So we're simply going to get this term here and divide it by that term there. And the solution to that is going to be x squared. So let's write that above our x squared term. Now the next step in long division is to now multiply our quotient, this quotient here, with our divisor. So we're going to multiply x squared with x minus 2. That equals to x to the third power minus 2x to the second power. And what we're going to do with that, we're going to subtract those quantities together. So we're going to get x to the third power and subtract it with x to the third power. Well, that's going to equal to 0. And we now have positive 4x to the second subtracted by a negative 2x to the second power. And that equals to a total of 6x to the second power. We're going to bring down the minus 16x, bring down the positive 8, and then again do this procedure over again. So now 6x to the second power gets divided by x, and that equals to positive 6x. So we line that up above the linear term, and we again go with the same procedure as before. We just simply follow the same steps. So we multiply this new term on our quotient with our divisor. So 6x times x minus 2, that is 6x to the second power minus 12x. And we subtract those two terms from the terms above. So 6x squared minus 6x, that's equal to 0. Negative 16x minus negative 12x, that's a total of positive 4x. Bring down the plus 8. And we then start over again. Now we have x minus 2. So now 4x is divided by x, which equals to positive 4. Oh, I'm sorry, that should be a negative 4. That should be a negative 4. So negative 4x gets divided by x, which is negative 4. So we're going to put negative 4 there and multiply our new term in our quotient with our divisor. Negative 4 times x, that is equal to negative 4x. And negative 4 times negative 2 is positive 8. And we are going to subtract those. So negative 4 minus negative 4, that's equal to 0. Positive 8 minus a positive 8, that's also equal to 0. So this last number right here, since we're at the very end, this is our remainder. And in this situation, because our remainder is 0, we can omit that, and we have our quotient. Our quotient is this here. So this is our quotient. This is our answer. Dividing these two quantities gives us, let me erase this, gives us the answer of x squared plus 6x minus 4. And this is how you use, again, divide polynomials using long division. Now let's simply divide the polynomials using synthetic division. Synthetic division is a short way and another technique in dividing polynomials. Now this only works if our divisor is x as a linear term, like x plus 7. as soon as I change the exponent on my divisor to 2 or 3 or anything else where this term is not linear, then this synthetic division technique does not work. Now we start our synthetic division by first having our division box upside down. And instead of writing all of the terms, we only focus on the coefficients. So here, instead of 6x to the third, we're only going to use the number 6, 40, -4, and +70. On the outside, our divisor, from x plus 7, we're going to get the opposite of this number and write it as -7. So we set up our synthetic division this way. Our synthetic division starts by bringing down the first term in our dividend, which is 6. And then we follow the same 2 steps. We start by multiplying this number with our divisor, -7. And then we add these quantities going downward. So we're going to add 40 with 42. And that gives us a total of -2. And then I repeat the process. I multiply now -7 with the -2. That gives us 14. And I add these things together, which gives us a total of 10. I multiply 7 with -7, with -10, I'm sorry, 10 with -7. That gives us a total of -70. And adding these two gives us a total of 0. So our solution here, well, let's discuss the last number. The last number is the remainder to the division. And in this situation, because there is a remainder 0, we could omit that. And our solution is going to be this. Dividing these, we're going to end up with 6x, but to the power of 2. It's always going to start 1 degree less than what the dividend started off with. Since it was degree 3, our quotient starts with degree 2, and then it just simply decreases in that order. So it's positive 6x to the second minus 2x to the first. Our last term is our constant, and because the remainder was 0, we could omit the remainder and ignore that, and this right here would be our solution. This would be the quotient of 6x cubed plus 40x squared minus 4x plus 70 divided by x plus 7. Let's see, try the next example by yourself. So pause the video. And, well, actually, no, you know what? Hold on. Let's look at this example right here because this one is a little bit different. Notice that we still have our divisor is a linear term. Notice that we have x to the first power, so we can use synthetic division. But there is going to be something different here because our linear coefficient is not 1, it's a 2. So we're going to set up our synthetic division by putting our division box upside down. We're going to use the numbers 2, 5, -19, and -42. And on the outside, we're going to use -7. But since the leading coefficient in our divisor is a 2, that -7 is going to be written over 2. It's being divided by 2. Now, other than that, the procedure is still the same. I start by bringing down the first term, 2, and I multiply this term with this number right there. So 2 times -7 over 2, that's equal to a total of -7. Adding 5 with -7, that's equal to -2. And again, I repeat the process. Multiplying these, that gives us a total of +7. And adding this gives us 12. Multiplying 12 with -7 over 2, that's equal to a positive, oh sorry, this is -12, not +12, -12. Multiplying -12 with -7 over 2, that gives us a total of +42. And adding that with the -42 gives us a remainder of 0. So the last value is 0. So our solution here is not going to be these numbers right here, all right? Now, since our leading coefficient was 2 and I divided the -7 by 2, I have to do the same thing with these 3 values there. I simply have to divide these 3 terms. Okay, so like I was saying, now we have to divide it by 2 because we are dividing again this value by that 2. So we have to do the same thing again to those values there. Not out of the remainder. The remainder, even though it's 0, that again doesn't get divided by this value here. So if this remainder was not 0, like if it was the number 4, the 4 doesn't get divided by 2. it's still going to just stay as 4. But these three values, again, the quotient parts, not the remainder, get divided again by that coefficient, the leading coefficient of 2. So we end up with 1, -1, and -6. So our quotient would be 1x to the second power. Since our dividend started with the degree 3, our quotient would be 1 degree less. So x to the second power minus 1x minus 6. And again, our remainder is 0. So this right here would be our answer. Let's see. This one, pause the video and try this example yourself. So let's check your work. So we'll start by first, inside our division box, let me make it kind of long, we're going to write 45, 89, 7, -82, and -48. And on the outside, we're going to write -6, and since the leading coefficient of our divisor is 5, that -6 is divided by 5. So let's start by bringing down the 45, and we'll multiply 45 with -6 over 5. That equals to a total of -54. Adding this is equal to 35. Now let's multiply 35 with -6 over 5. You know what? I forgot to add my calculator here. So let's add the calculator. So alpha y equals our fraction -6 over 5 times 35. That's equal to -42. Let's add 7 to that, and that's equal to -35. Another way of multiplying the -35 times, we can write it in parentheses. Instead of hitting alpha y equals to write the fraction, we could just simply use parentheses and write -6 divided by 5. That's the same thing as -6 over 5. And that equals to +42. Now that +42 is added with a -82, and that's equal to -40. And let's multiply that answer with -6 over 5, which is equal to 48. And this gives us a remainder of 0. Now, all of these numbers have to be divided by 5. And we end up with 9, 7, -7, and -8. So our solution is 9x to the third power plus 7x squared minus 7x minus 8. All right. Now let's look at an example where we are missing powers. Notice on this example, our dividend has x to the third power, has x to the second power. It does not have an x to the first power, and it jumps to the constant, the one without the x. So we have 4x to the third, we have 40x to the second, but there is no x to the first power. That means that we have to use a 0 for that placeholder. In order to use synthetic division or even long division, we have to keep account for all of the powers from the largest one to the smallest one, which is going to be the constant. So if any one of these powers is missing after 3, 2, 1, or constant, we use a 0 for that placeholder. And in this situation, we're only missing the x to the power of 1, so we're going to use 0 as that placeholder. And we have our constant of -2. On the outside, we'll write -10, the opposite of adding 10. So we'll write -10, and since the leading coefficient is 1, this is being divided by 1, which is just simply going to stay as -10. So we're going to bring down the 4, and multiply 4 times 10, which is negative 40. This adds up to 0. Multiplying 0 times 10 is 0, and adding 0 with 0 is 0. 0 times negative 10 again is 0, and adding negative 2 with 10 is negative 2. So here, our answer is going to be 4x to the second power plus 0x to the first power plus my constant of 0. And since this last number here is the remainder, let me show you how we write a remainder now that we actually got a remainder that is not 0. So we're going to add this remainder of negative 2, and we write it over our quotient of x plus 10. So this is going to be our solution. Now, in this situation, since these two terms are 0 terms, we can omit those and kind of just skip over them and write this answer as simply as 4x squared plus the remainder of negative 2 over x plus 10. Because it's redundant to write 0x and then add 0. Because again, we're adding 0 terms, so there's no reason to actually write them out. And we can simply write that solution as this. They're both equivalent and they're both considered to be correct, but this is a better way of writing, again, this notation there. So let's look at this example right here. This example number 6 isn't missing any powers. Notice that we have x to the fourth power, x to the third, x to the second, x to the first, and then our constant. So here we're not missing any powers. So we'll write negative 5 on the outside. One, negative 4, negative 49, negative 25, and negative 19. Again, multiplying and adding. So here I multiply 1 with negative 5, that's negative 5, and adding negative 4 with negative 5, that's negative 9. Negative 49 plus 45, that's equal to negative 4. Multiplying that answer with negative 5 is equal to 20. Adding it with negative 25, that's negative 5. And multiplying that answer with negative 5 is equal to positive 25. Adding the negative 19, we end up with 6. So our solution here, because our leading coefficient is 1, all of these numbers get divided by 1, which doesn't change anything, and we end up with 1x to the third power minus 9x to the second minus 4x to the first minus the constant of 5. And since this last number is the remainder, we add the remainder over x plus 5. And notice again that my quotient is 1 degree less than that value here. So x to the fourth, our quotient is x to the third. Now, besides powers again having to be again have a place for every power, here we have x to the fourth, x to the third, x to the second, x to the first, and the constant. They also have to again be in order. So like in example number 7, notice that our powers are not in order. X to the third, the highest exponent, 3, is not in the very front. So we have to rearrange this so our degrees are in order from highest to lowest. So x to the third, to the second, to the first, and then our constant at the very end. And since no powers are missing, we're not going to use 0 as a placeholder. So here, this will be divided by x minus 1, which means we put a positive 1 on the outside. And on the inside, we put positive 6, negative 2, positive 3, and then negative 2 in that order. If you put it in a different order, you're going to end up with the wrong answer. So start by bringing down the 6 and multiplying 6 with 1, that's equal to 6. Add that with a negative 2, that's 4. Multiplying 4 with 1, that's equal to 4, and adding it with 3, that's 7. 7 times 1 is 7, and 7 plus negative 2 is 5. So our solution here is 6x to the second power plus 4x to the first power plus 7. And our remainder, 5, gets added over our divisor of x minus 1. So here is your solution. Let's see. Try this example yourself. Rearrange them, and then come back and check your answer. So let's see here. Let's check your work. So the highest exponent is 4. So this term would have to be first. And then after x to the 4th power, we need to have an x to the 3rd power, which is 26. After x to the 3rd, we need an x to the 2nd, which we have, negative 24. We need an x to the 1st, which we have, that's the positive 8. And then at the very end needs to be our constant, which we also have, the negative 45. If any of these powers were missing after x to the 4th, then we would use a 0 as a placeholder. But since none of them are missing, we don't have to do that. Now on the outside, we're going to put a positive 9 because it's negative 9. We're going to put a positive 9. And since the leading coefficient is 7, we put that over 7. So we divide it by 7. So we start by bringing down the 7. And we're going to multiply 7 with 9 over 7. So 9 divided by 7. That's equal to 9. So 9 goes here. We add that 9 with 26, and that gives us 35. Multiplying that 35 with 9 over 7 is 45. Adding it with negative 24 is 21. And multiplying that answer with 9 over 7 is 27. Adding that with 8, that's equal to 35. And well, we know that 35 with 9 times 9 over 7, that's going to equal to positive 45. And I know that because I already did it again before. This times that gave me that 45. So if I do 35 times that, that's going to get the same number, 45. And 45 minus 45, well, that's equal to 0. So we'll have a remainder of 0. So our solution here isn't going to be this, because remember, we had it dividing by 7. So I have to divide these values all by 7, which are going to be 1, 5, 3, and 5. So our answer is 1x to the 3rd power plus 5x to the 2nd plus 3x to the 1st, and then my constant of 5. So this is your solution. All right. Now let's use an application. Let's use an application to the synthetic division or long division, which is the division algorithm. Now what the division algorithm is basically saying here, that if we have two polynomial functions, f and d, where d of x is not the 0 polynomial and the degree of the d of x is less than or equal to the degree of f of x, then there's a unique way of writing the polynomial f of x as the product of q and d plus a remainder r, as you see right here. Now, what this is essentially just telling us is that any polynomial can be written as the product of a divisor and a quotient plus a remainder. And this makes more sense again if we're looking at values, at numbers. For example, the number 30. The number 30, for example. The number 30 can be written as 3 times 10 plus a remainder of 0. Or I can write the number 30 as 4 times, let's say, 8, which is 32, plus negative 2. You see how that equals to 30? So what this division algorithm is essentially saying is that any number, along with any polynomial, because that's what a polynomial is just a long way of writing a number, can be written as a product of two things plus a remainder, again, of a positive or negative value. It doesn't matter. So another example, 30 is writing it as 2 times, let's say, 7 times 3, which is 21, plus 9. So you see, I can write 30 in an infinite number of possibilities as the product of two things plus a remainder. Whether that remainder is 0, a negative number, or a positive number, there is a way of writing again the number 30 as the product of two values plus a remainder. Now, if this is true about, again, integers, then it's also true with polynomials. So we're going to use the division algorithm to represent a function as the product of a quotient and a divisor plus a remainder r of x. So for example, here, let's use the division algorithm to write f of x as the product of x minus 4 times some quotient plus a remainder. So what we have to do is, using synthetic division, figure out what that quotient is. So using positive 4 on the outside and 1, negative 1, negative 14, and 11 on the inside, using synthetic division, we end up with 1 times 4, which is 4, 3. 3 times 4 is 12. This is negative 2. And negative 2 times 4 is negative 8, which is positive 3. So this one right here is my remainder. So this is my remainder, which we'll call, again, r of x. And this is my quotient, q of x. So q of x is equal to 1x to the second power plus 3x minus 2. And my remainder is 3. So using the division algorithm, what this means is that I can write f of x, which is x to the third power minus x squared minus 14x plus 11. This is equal to x minus 4 times the quotient of x squared plus 3x minus 2 plus the remainder of 3. So if I multiply these two things together and add 3 to that, I end up with this polynomial there. So this is what the application to the division algorithm is, to synthetic division. This is one application that we use synthetic division for in order to represent a polynomial as the product of two things plus a remainder. Let's see. You try this next example by yourself. Use the division algorithm to write f of x as the product of d of x times q of x plus a remainder. Let's see. Let's check your work. So we're going to write negative 2 on the outside. We have 15, 10, negative 6. But notice that we skip from x to the second power to our constant. We don't have an x to the power of 1. So that means we're going to have to use 0 as a placeholder for that. And then 14 at the very end. So we have, again, our x to the third. We have an x to the second. I'm sorry. X to the fourth. We have an x to the third, an x to the second. We do not have an x to the first power. That's why we're using 0. And then at the very end is our constant. So let's bring down the 15 and let's multiply. So this equals to, let's get our calculator out here so I don't make any mistakes. So 15 times negative 2, that's negative 30. We're going to add 10 to that, and that's negative 20. Multiply that with negative 2, that's 40, plus negative 6, that's 34, times negative 2, that's negative 68, plus 0, that's negative 68, and times negative 2, that's equal to 136, plus the 14, that's equal to 150. And that right here is my remainder. And this is my quotient. So q of x is 15x to the third power minus 20x to the second power plus 34x to the first, and then the constant of negative 68. And my remainder is 150. So what that means, according to the division logarithm, is that I can write f of x this f of x is equal to x plus 2 times 15x to the third minus 20x to the second plus 34x minus 68. So multiplying those two together and adding the remainder of 150 is going to give me this polynomial there. So this is my division, the setup of my division algorithm. So writing it, multiplying these two things and adding 150 is equal to this. Okay, well, this concludes again our lesson on 2.4, dividing polynomial functions. Now, even though I only did one example of long division, you'll find it again a little bit more convenient to use synthetic division. Just recall again on the situation that synthetic division only works if our divisor, again, our divisor is a linear term, and if our linear coefficient is not 1, we just simply have to divide it by that coefficient. If it is 1, technically you can divide by 1, but it really doesn't affect the overall answer because dividing by 1 keeps things the same. But as soon as this degree is not 1, it's not a linear, not x to the first power, but it's x to the second, x to the third, or something else, then you have no choice but to use long division in order to divide these things out. Okay, well, that concludes again this lesson. Again, if you have any questions, send me a message or remind or through email, and I appreciate you watching, and I hope you have a great day.